Hello guys, once again welcome to the SQL tutorial video channel. So actually I maybe should rename this channel to database channel or something like this, because in the end we're just dealing about database stuff. So what we're gonna do this time, will be a lesson about how is a database structured. That means how are the objects actually structured in a physical way. So we already know, and if you don't know, please have a look at those videos here about clustered and non-clustered indexes. So we know about the logical structure, but how is this all stored on disk? So before we go into this way, we have to consider a different kind of table, that is a heap table. I don't want to go really deep into heap tables in this session, but just it's basically very simple. So while in a clustered index we have this B tree in place, in a heap we don't have anything in place, so we have just data pages. Let's take a look. So while we have a B tree in place with a root page, and then we have intermediate pages, and in the end we have data pages, and as a leaf pages where the data actually is stored. This would be a typical clustered index. On a heap it's a little bit different. On a heap we have just pages, so we have just data pages where the actual data is stored. It's completely more or less random, so there is no physical order like we have it in the clustered index, where we here have the order of the primary key on the leaves with double linked lists. We have no such lists here, and therefore we have also no logical order, no linkage between the data pages. This is a heap. And how do we find rows in a heap? This is now the question. So how is the structure of the database objects actually created? So let's do a bottom-up thing here. So we start with where the data row is actually stored. So we have a data page. A page in a SQL Server is always 8 kilobyte big, and we have different kinds of pages. We have a data page, and what's up with this fly here? We have a data page, we have also index pages, we have page free space, we have GS global store page, we have the SGAM, the GAM page, and so on and so forth. But we are focusing now on data pages. In a data page, or it is actually not a data page but an in-row data page. Here we have all the objects stored in a table that are if of type in-row. That means this is no binary data, no large object data. That means no text, no binary, no image data type, and also no user-defined data type. But we have all rows that are below 8 kilobytes in width. We have in-row data. So there's also line large object data. What I stated already, this is of type text or image or whatever user-defined data type we have here. And then we have also the pages that are row overflow pages. Those hold data for rows that got bigger than 8 kilobytes. Since one page is only 8 kilobytes, we cannot store this row in one page, so we have to take row overflow data. I won't focus on those two, we are just focusing now on in-row data, hence I will delete those two. So I don't really want to get into detail on what byte, what header byte you can find what information. You can look this kind of things up, but in the end we have a page header that is of 69 bytes always. Whatever there is written, how many free space I have here, and so on and so forth. You can have a look there in the literature. It would take too long and too boring to the video. And then we have the actual data rows, and in the end we have an offset area that basically links to the correct row. So the rows don't have actually numbers but have offset addresses where you can jump to the correct row that you want to have. So this is a basic data page. So for clustered indexes and also for heaps, every data is stored in such a data page. First question that is open now is how is a clustered index structured, we have more than just data pages. We have those intermediate and this root node page. What is that? So this is actually an index page. So an index page is used for a non-leaf clustered index or for a non-clustered index. A non-clustered index, remember, holds no data or no data by default, but just links or include columns and such things. But this is all stored in an index page. So an index page is basically the same thing again. We have a page, we have as well 69 bytes of header, and here for indexes typically we have always a key value, and we have a pointer. So of course for B-tree we need to know in which key value we have to jump to the next level beneath this level of clustered index, and you have many key value pairs that basically are pointers. Please if you know how clustered index is structured, you know what I mean. So those pages don't hold actual data, they hold basically a key value area and a pointer to where can I find the underlying page in the underlying level of the clustered index when following this pointer. So the root node is the same thing, it's just an intermediate node, and as I told you, for a non-clustered index on a clustered index table you have as leaf index pages as well that just tell you this is the clustered index key you now have to look up if you want to have the full data page row, the full data row. Okay, and for heaps you don't find the clustered index key in the leaf node, but you find for non-clustered index you find the row identifier. But it's the same thing, it's a pointer, you have to follow the pointer to find the actual row. So now the question is, what is with the heaps? I told you there is no structure for this heap. So the heaps are also structured in a little bit of context, like in a page that is called an IAM, an index allocation map. But before we come to the IAM, we just want to we want to know another thing. So what happens if my table is completely empty and I write the first row in it? Where does the page come from? Where is the page located? What the hell happens then? So to know that, we need another concept for our data pages. So we know already a data page is always 8 kilobyte in size, and here comes another thing. There is something, this is a page, and there's something called an extent that is basically consists of 8 pages. So hence it is 64 kilobytes in space. So imagine this as a container. You have 8 buckets here, 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 buckets, and this is an extent. So there are 2 types of extents. The first is a uniform extent. That means we're talking about a table called table 1, and if every page of this extent is owned by table 1, this is called a uniform extent. Okay, so this is uniform extent if it belongs to exactly one object. It may be a table or also an index. But there's a second form, that is a shared index, a shared extent. And a shared extent, of course, is then an extent that shares data pages. That means page 1 may be from table 1, page 2 may be from another table, page 3 may be from another object like an index or something like this. So if this happens, we have a shared extent, and this is the first thing that typically gets allocated or when you insert a row into a new table. So we have to remember, we have to recall the following thing. A table, when it gets written first time, allocates a page, most likely in a shared extent. That means the first up to 8 pages, up to the first 8 pages can be in shared extents. Okay, 8 pages, or better here, 8 pages can be in a shared extent. Then what happens after? Then what happens when we allocate the 9th page? Okay, the 9th page will be a uniform extent, because SQL Server always allocates uniform extents after the first 8 pages. This is due to reducing complication and over allocating memory when we only have very small tables that don't need more than 64 kilobytes in approximately in data. But for bigger tables we have uniform extend. So now we come back to IAMs. Now we know extends and we know the allocation strategy. That means the first 8 pages can be on shared extends, but from then on we always use uniform extends. Now we have to reconsider what an IAM is. So I had to cut the video at this point because I got overly excited. We won't cover IAM pages here, but in the next video. Thank you for watching. Please subscribe to my channel and leave comments in the comment section. Have a good day.